This video is going to cover section 7.2 on the central limit theorem for sums. So the central limit theorem for sums states that suppose x is a random variable with a distribution that may be known or unknown. It can be any distribution, so that's the good thing about the central limit theorem. And suppose that mu sub x is the mean of our original random variable x, and sigma sub x is the standard deviation of our original variable x. Then, if you draw random samples of size n, as n increases, the random variable, the sum of x, so remember this symbol here is the Greek letter, it's the uppercase S, it stands for a sum, consisting of sums, tends to be normally distributed, and the random variable, the sum of x, is normally distributed with a mean equal to n times mu sub x, so that is the sample size, times the mean of your original random variable, with a standard deviation of the square root of n times the standard deviation of x. And so the standard deviation of your sample size, the square root of your sample size times the original standard deviation. So basically, if you repeatedly draw samples of a given size and calculate the sum of each sample, these sums tend to follow a normal distribution. As the sample sizes increase, the distribution of sums more closely follows the normal distribution. So this normal distribution has a mean equal to the original mean times the sample size. So that's what that looks like. Mu sub sigma x equals n times mu sub x. And a standard deviation, or remember we also call it the standard error, equal to the original standard deviation times the square root of the sample size, which looks like this. So sigma sub sum of x equals the square root of n times sigma sub x. The random variable sum of x has a z-score that looks like this. So again, remember, this is just one of our data values, so one sum of x's minus the mean of that distribution, which is n times the original mean, divided by the standard deviation of our new distribution, which is the square root of the sample size, times the standard deviation of the original distribution. And the sum of x is one of those sums that we sample. So example 7.5, an unknown distribution has a mean of 90 and a standard deviation of 15. A sample of size n equals 80 is randomly drawn from the population. So we're going to find the probability that the sum of the 80 values or the total of the 80 values is more than 7,500. So sometimes this is like hard to get your mind around when we've just been talking about sample means, okay? So this is sample sums. So we take a sample of a bunch of our data values and we add them together. So that's one reason why we get big numbers here in this section. We're also going to find the sum that is 1.5 standard deviations above the mean of the sums. So when you think about part A, the probability that the sum of the 80 values is more than 7,500, again, the central limit theorem tells us that these sample sums are going to be normally distributed. So we're going to use the normal distribution to figure out this probability. So our new mean is n times the original mean, so 80 times 90, 7,200. Our new standard deviation for our sample sums is the square root of our sample size, square root of 80, times our old standard deviation, 15, which in this case is 134.164. And we're doing a probability that the sum is greater than 7,500, so we're going to do 1 minus. So I'm going to go over into Excel. And we're going to do 1 minus the normal distribution. So we're looking, as you can see over here, greater than 7,500. So this is the first number we put in. The mean of our sample sums is 7,200. Our standard deviation, remember here, we can either put in this number, which is going to have some rounding error in it, or we can type this little equation expression into the normal distribution and use that. So we could say SQRT of 80 times 15. You could do 15 times the square root of 80, whichever makes more sense to your brain. Or you can put in that 134.164. or you could use a cell reference if you want, and then we're going to use the word true. And we get about 0.0127, or 1.27%. So what I mean about that cell reference is down here you could say, like, let's calculate the new standard deviation, and I'm just going to write new standard deviation instead of doing all the special symbols and stuff. But you could just type in 15 times the square root of 80. Okay, so that's the 134.164 from the slide. But then in the formula here, you could delete what I typed before, and I could just reference this cell. I'm going to get the same information. So again, whenever you're doing these problems, like, do it in a way that you understand for your brain, that maybe it's step by step, or maybe it's all together. It doesn't, one way is not better than the other. It's just how you remember it and how it makes sense to you. So now find the sum that is 1.5 standard deviations above the mean of the sums. So in this case, we're going to use, the raw score formula. So where the sample sums are going to be the z-score times the standard deviation plus the mean of the sample sums. So 1.5 times that standard deviation plus 720, 7,200, which is our new mean. So we get 1.5 times 134.164 plus 7,200, and we get 7,401.246. So if you were going to do it in Excel, it would look like 1.5 times, now we're using the standard deviation, which is down here, so we can just use that cell reference, and then plus that sample sum mean, or the mean of the sample sums. Okay, so 7,401 is 1.5, 1.5 standard deviations above the mean of the sums, or to the right of the mean of the sums. Try it 7.6 from the book. In a recent study reported on October 29th, 2012 on the Flurry blog, the mean age of tablet users is 35 years. Suppose the standard deviation is 10 years and the sample is of size 39. What are the mean and standard deviation for the sum of the ages of the tablet users? So we looked at the mean from this question before. What's the distribution? Find the probability that the sum of the ages is between 1,400 and 1,500 years, and find the 90th percentile for the sum of the 39 ages. So again, we're going to calculate the new mean, the mean for the sample sums. So we take the sample size n times the original mean, and in this case we get 1,365. We calculate the new standard deviation for the sample sums, which is the square root of the sample size, times the original standard deviation, and we get 62.45. What is the distribution? Remember that the central limit theorem tells us that the sample sums are going to be normally distributed. So we can use the normal distribution formula to find the probability that the sum is between 1,400 and 1,500 years. So over to Excel. Here I put in a little space to calculate the mean. Okay, so remember for sums, the mean is going to be the sample size times the old mean. So you would just do 39 times 35. And then the standard deviation is the square root of the sample size times the original standard deviation. Excuse me. And so I have it here in the slide, but it can be helpful to put it in Excel, because when you're then doing those normal distribution formulas, you can just reference that cell if you like doing it that way. So remember, our between formulas are going to be the bigger one, so that's 1,500. Here's our mean, so I'm just going to click on that cell reference, and then the standard deviation, click on that cell reference and use the word true. And then I'm going to subtract off the normal distribution, the probability that we're less than the 1,400. So that's the number from the problem. And then again, I'm going to use that same mean and that same standard deviation, and the word true. And I get 0.2727, or 23, sorry. So the probability that the sum of the ages is between 1400 and 1500 years is 0.2723. And the 90th percentile for the sum of the 39 ages. So percentiles, when we're looking for a percentile, we're going to use the norm.inv formula. And the probability is 0.9. Again, the mean and the standard deviation are what we just calculated. So again, if you like using the cell references, I think it can be really efficient. And then there's less chance of typing in a mistake or making a mistake when you type something in. So the 90th percentile is 1,445.03. So that means that 90% of our ages, the sum of the ages is up to and including 1,445.03. So this is example N, the try at 7.7. I had a couple of pieces in it that I thought might be helpful. So the mean number of minutes. So I think like that last one where you're like adding up the ages, can't think off the top of my head where that might be super realistic. But this one, the mean number of minutes for app engagement by a tablet user is 8.2 minutes. Suppose the standard deviation is 1 minute and you take a sample of size 70. So now we're talking about adding up all of the engagement minutes. So I think, to me, that just makes a little more sense, or, seems a little more realistic that you might want to add up all of the mean engagement minutes and know what those sums are. So there's different cases where different things make sense. So what are the mean and standard deviation for the sums of the times? Find the probability that the sum of the sample is at least 10 hours. So that's going to be greater than 10, greater than or equal to. And find the 95th percentile for the sum of the sample and interpret this value in a complete sentence. So mean and standard deviation. So we know that the mean for our sample sums is going to be equal to the mean of our original variable, 8.2, times the sample size, 70. I think last time I did it as 70 times the mean. Okay, so that's our new mean. And our new standard deviation is the square root of that sample size times, I think it was 70, yeah. And the standard deviation here is 1, times 1. So we get 8.37. So calculate your mean and your standard deviation. Again, you don't have to do that part in Excel, but it is helpful if you want to use the cell references when you use the normal distribution formula. So our new mean, the mean of the sample sums, is 574, and the standard deviation of the sample sums is 8.37. So we're going to find the probability that the sum of the sample is at least 10 hours. So look what I did here. And this was a good thing to point out. So if the sum of the sample is at least 10 hours, but everything else that we're doing in the problem is in minutes, we need to convert our problem, 10 hours, into minutes. So we want to know what the probability that the sum is greater than 600 minutes. If you use the 10 in there, you're going to get the wrong answer. It's a greater than problem, so it's 1 minus the normal distribution and of 600 minutes. Our mean is 574, our standard deviation 8.37, and our word true. So, very small probability that the sum is greater than 10 hours. So 0.0009 or 0.09% probability that the sum of the sample is greater than or equal to 10 hours, at least 10 hours. Again, the percentile problems, we're going to be using the norm.inv formula. So norm.inv for the 95th percentile, 0.95, a mean of 574, our standard deviation of 8.37, and we get 587.76. So 95% of our sums, of our sample sums, are less than or equal to 587.76 minutes. So 95% of sums of app engagement times are at or below 587.76 minutes. So we know this information. What is the probability that the sum of the sample is between 7 hours and 10 hours? What does this mean in the context of the problem? So again, we have to convert the hours into minutes because our mean and standard deviation are in minutes. So 7 hours times 60 minutes is 420 minutes. And then we know that 10 hours is 600 minutes, 60 minutes times 10 hours. So we're going to do the that distribution of 420, use the mean from above and the standard deviation and the word true, minus the normal distribution for 600. So we know this one, we actually could just, well, we can't because we had the greater than 600 before, and so we don't want to just use that cell reference. I was going to try to have a little shortcut, but it wasn't going to work. So I took the mean and the standard deviation, and I'm going to use the word true. And I got a negative number. What did I do? So our probability should never be, oh, because I did the smaller one before I did the bigger one. That was very not smart, but the negative caught, like that, so how I caught my error. So probability should always be positive. Z-scores can be negative, but not probabilities. All right, so I put the bigger one first, and then I subtracted off the smaller one, and now we get a positive value. It's the same value, just the signs were different. So 0.9991. So that's a pretty high probability. There's almost 100% probability that the sum of minutes of app engagement is between 7 and 10 hours, or you could say 420 minutes and 600 minutes. Find the 84th and the 16th percentiles for the sum of the sample and interpret these values in context. So remember when we're doing percentiles, we just did this. It's the norm.inv. What's the probability that relates to the 84th percentile? So 0.84. Remember, we just moved that decimal place 2 to the left. We're going to use the mean 574 and the standard deviation. We get 582.3. And then the 16th percentile, so it's just the same formula, but we're going to use 0.16 and then our mean and our standard deviation. So the 84th, so 84% of our app engagement sums are less than or equal to 582.3 minutes, and 16% of our app engagement sums are less than or equal to 565.7 minutes. So that's what we mean in the context of the problem. So here we have that information. So that's the end of the video for 7.2, which was on the central limit theorem for sample sums.